Hi, I'm Harry Porter. In this video, I'll describe the instruction set architecture of the Blitz-64 computer system. Here is a very generalized picture of a computer system. I'll be describing what goes on inside the Blitz-64 core. In particular, I'll talk about all of the registers that are visible to software. I'll describe the assembly language, and I'll talk about how assembly language instructions are translated into binary machine code that can be executed directly on the hardware. The instruction set architecture is essentially the boundary between the hardware and the software. Low-level systems programmers write software that runs directly on top of the bare hardware, while hardware engineers design circuits that meet the boundary and will execute the software directly. Other examples of instruction set architectures are the Intel x86-64 architecture and the ARM architecture and the RISC-V architecture. Blitz-64 is different than all of those, and I will tell you all about it. Before we get started, I want to talk about the overall Blitz project. It consists of several components, including the instruction set architecture, the hardware that implements that architecture, and software that runs on that hardware, as well as documentation. The check marks here indicate the components that are essentially complete at this time. So there is the design of a completely novel instruction set architecture, which I'll be describing in this video. We've got some hardware to implement this architecture, or at least the beginnings of it. There is a software emulator that emulates instructions, that is a virtual machine that's capable of running large and complex Blitz software. There's also an FPGA implementation written in System Verilog that executes Blitz instructions. In the future, we hope to see a single board computer, and who knows what's beyond that. As far as the software goes, the assembler is the lowest level piece of software. There are some additional related tools, linkers and so on, and these are complete and functioning. The project also includes an entirely new and novel programming language called KPL, which stands for the Kernel Programming Language. This language has been designed, and the compiler for it has been written, and the language is up and running. Still in the future, we have operating system stuff. The documentation, we're keeping on top of that, and in particular, the document that you need to look at that corresponds to this video is called the Blitz-64 Instruction Set Architecture Reference Manual. The Blitz architecture is a 64-bit architecture. All the registers are 64 bits in length. There are 16 general-purpose registers. There are 16 registers which are called control and status registers that have special uses and special meanings. Of course, there's a program counter. There are a number of instructions that support virtual memory and virtual address spaces. Among other things, we have what are called translation look-aside buffer registers, and I'll talk about those later on. And the instructions come in two sizes. The full-size instructions are 32 bits in length, but we also have compressed instructions, which are 16 bits in length. So I'm going to be covering all of the instructions, not in great detail, but I'll introduce essentially every instruction. Let me go over some of the terminology that's used in the Blitz project. Of course, a byte is 8 bits, shown here. We use the term half word for 16-bit quantities, and we use the term word for 32-bit quantities, or 4 bytes, and the term double word for 8-byte quantities. Blitz is a 64-bit architecture, as you might guess from the name, so our primary data type is the double word. And we oftentimes express the double word value in hex. It's rather lengthy, but it's certainly a lot shorter than in binary. The assembler will accept either hex or decimal, so quite often we express quantities in decimal with the assumption that anything expressed in decimal is really a short form for a 64-bit binary quantity. Of course, binary numbers are often represented in hexadecimal. Hex is a good representation for binary numbers because there's an exact correspondence between each hex digit and 4 bits in a binary number. It's much easier to talk about a double word using 16 hex digits than 64 binary bits. Here's the one-to-one correspondence, as I'm sure you're familiar with, between 4 bits and 1 hex digit. And here's an example of well, this is a half word, 16 bits. The Blitz architecture and the KPL programming language are strongly biased in favor of using 64-bit double words. With a signed double word, the range is really quite large. Here is the exact range that you can get with a signed 64-bit number. Double words are also used for storing double precision floating point numbers. Floating point is basically a computer representation that approximates scientific notation. The range is even larger, but the precision is limited. Here's the largest number approximately, and the smallest number above 0 is really quite small, with an accuracy of about 16 digits. Floating point representation also has the capability of representing positive and negative infinity and things that are not numbers. It's really quite a complex domain to study. We're not going into it much in this video. Let me comment on the difference between 32-bit numbers and 64-bit numbers. 32-bit numbers are just not large enough for some very practical applications. You cannot represent the Earth's population. You cannot represent the federal debt, or the milliseconds since 1970, or even the number of bytes in the memory of a cell phone. So 32-bit numbers really fall short, and Blitz considers the 32-bit values to be completely legacy. 64-bit numbers are, on the other hand, very useful, and they can represent almost anything that you would really want to count. For example, the astronomical unit, which is the distance between the sun and the earth, could be represented to great precision in a double-bit integer. The seconds since the Big Bang, or the world GDP in hundredths of a cent. These are things that we can't even count accurately, so it's a really adequate range of numbers. Blitz also favors signed numbers, and every double word is assumed to be signed. So you might ask, why don't we have unsigned numbers? And unsigned numbers have been explicitly left out of the Blitz design because of all kinds of problems with them. Unsigned numbers basically outlaw negative values, and that's just anti-mathematical and leads to all kinds of problems. And furthermore, with 64-bit numbers, you have plenty of positive numbers, so there's really no need to eliminate half of the integers. Okay, let's take a look at our first Blitz instruction, and we'll look at the add instruction. Here it is expressed in assembly language, and you see that every assembly instruction has several parts. First, there's the opcode, and then there are the operands, in this case 3 registers. And finally, you have a comment, or hopefully you have a comment. And in this case, the add instruction is just adding the contents of 2 registers and putting them into register 7 in this particular example. Assembly code is human readable, although large assembly programs are very difficult to read, so commenting is critical. With assembly language programs, there is exactly 1 instruction per line. Okay, so there's no complex syntax like there is in other high-level languages. A compiler will take source code in a high-level language, such as the KPL language, and will transform or compile it into assembly code, which can then be executed. The computer just executes instructions like this, very simple add instructions that work on registers, whereas the high-level language code can do more complex things, complex expressions, and so on. The assembler tool is then used to take the assembly language program and convert it into machine code. So the output from the compiler is fed into the assembler, and out comes the machine code. Machine code is binary, and it's not human readable. It's meant for the computer. This is the binary bit pattern that will actually be produced for the add instruction that we saw above. So it's an instruction which is 32 bits long, and you have some of the bits reserved for the opcode. In this case, this add happens to be what you see here. And you've got the registers encoded into this instruction as well. This is hard for us to understand, and we might be more comfortable expressing it as hex. Well, the machine code is then loaded into memory at runtime. When you're ready to execute the program that contains this add instruction, you would put these bytes, these 4 bytes, as well as other instruction bytes, into memory, and the core would then execute the machine code instructions. So assembly code is human readable, and every assembly instruction is translated into a binary machine code, which can be executed by the computer. Next, let's look at the general purpose registers. The registers are 64 bits, and there are 16 of these registers. They are general purpose in the sense that every instruction can specify any register. Many of them have special uses, but these uses are by convention. Nothing in the hardware makes any register special, with the exception of register R0. R0 is always 0. But otherwise, the core doesn't really know about how the registers are used. So let's take a look at these 16 registers and how they would be used, although, as I said, the core doesn't have any special hardware for these particular uses. So here I've listed the registers by their primary name, R0 through R15. Some of them have secondary alternate names, and these alternate names can be used in the assembler. Either is okay, but of course we recommend you use the alternate name because it makes it more clear. R0 is unusual in that it is treated specially by the hardware. Its value is fixed at 0 and it cannot be modified. R1 through R7 are your main primary work registers. They're used for passing parameters and storing local variables in a function, for example. T is a temporary register. We'll talk about how it's used a bit later. S0 through S2 are additional supplemental work registers. And the last 4 registers, well, starting at the bottom, R15 is the stack pointer, SP. And then we have the link register, which is used in subroutine calls. And then we have 2 pointers, the global pointer and the thread pointer. These registers don't change very often, and they are used to point to data areas, and they make addressing a little bit more efficient. The add instruction we just looked at used only registers, but there's another form of instruction which uses literal or immediate values. That is, a value is included directly in the instruction. So here's an example. The instruction is the add immediate instruction, and here's the opcode. And in the first example, we see that the contents of R1 is added to a particular value expressed in hex. Here, the comment shows the decimal equivalent. And we can encode the value either in hex or decimal, whichever is easiest, in the assembly code. And the assembler can deal with either hex or decimal or, in fact, more complex expressions. The destination register for all instructions is always on the left. It's sort of like it is in any assignment statement. The assignment goes to the left. So note that these are both doing addition, both doing 64-bit addition, but they have different opcodes. So they are different instructions. Each instruction has a unique opcode. And we also want to note that the assembly language has a very fixed format. In this particular instruction, the immediate value is the last operand here. Okay, you cannot specify it like this. Okay, the assembler will object to this, give you an error. We have to have exactly this form. Here is the machine code that would be generated by the assembler for that add immediate instruction. In this case, the opcode only occupies the first 8 bits. We have the 2 registers, the destination register, which happens to be R6, and the source register, which happens to be 1 in this example. They're located right here in the instruction encoding. And finally, that leaves 16 bits for the immediate value. Okay? We can specify this entire machine instruction in hex if we want to. 0, 1, 1, 2, 3, 4, 1, 6. Because the instruction has only 16 bits for the immediate value, the immediate value has a limited range, and in particular it can be any number between minus 32,768 and positive 32,767. That is, any signed number that can be represented in 16 bits will be usable in this instruction. So far we've seen 2 instructions, the add instruction and the add immediate instruction. And we've shown how they are translated into binary machine code. And so now we're going to talk a little bit more about the encoding of instructions into binary. Most instructions are 32 bits. In fact, all instructions can be represented with a 32-bit binary machine code. Some instructions can be represented with only 16 bits, and so we have a compressed instruction format that requires only 16 bits. The first 2 bits of the instruction determine whether it is a full-sized 32-bit instruction or a compressed instruction. Full-size instructions start with 00 always, and the remaining bit patterns are used for compressed instructions. So all instructions have a full-sized form, and some instructions also have a compressed form. So every compressed instruction has a full-sized way of expressing that same instruction, but not vice versa. So why do we have compressed instructions? Well, we want to reduce the code size. And so if we can reduce the code size, it means that we can increase execution speed. Typically, the computer spends a lot of time loading instructions. So by making the code size smaller, we can increase the performance. So what we want to do is encode the most frequently executed instructions in a compressed format. At this point in time, we've only fixed the full-size instruction encoding. We are delaying determining what the compressed instruction formats will be until later. We want to get some good performance data and analyze common applications to determine which instructions are executed very often and what instructions will yield the greatest performance benefit by being compressed. How are assembly code instructions translated into machine code? Well, there are only 4 different formats of machine code instructions, which we call A, B, C, and D. So let's take a look at each one of these in turn. Format A accommodates instructions that require only registers. There's no area for an immediate value. So we can have up to 4 registers, a destination register and 3 additional operands. The first byte is all zeros, and that leaves 8 bits for the opcode. We call this second byte op2. The first byte we call op1. So there are, of course, 256 different possibilities for format A instructions. So the opcode is encoded in this field here, and each of these 4-bit fields is adequate for one register, one of the 16-bit registers. The second format is B, and here we only have 2 registers, the destination register and a source register. And we have room for a 16-bit immediate value. So this was what the add I instruction was. The first 2 bits are always 0 of every instruction, of every full-sized instruction, I should say. And that leaves 6 bits for the opcode. So we have only 63 possible values for format B, C, and D instructions, because the 64th is used for format A. In format C, we have no destination register, and instead we have 2 source registers. Again, we have a 16-bit immediate value, and it's encoded in these bits here. Format D has room for only 1 register, the destination register, but it has a slightly larger number of bits for the immediate value, so we can represent a larger range of values. Reg D, we'll use that notation for the destination register, and the source registers we'll call registers 1, 2, and 3. Okay, and again, any of these fields can contain any register. With a 16-bit immediate value, we can only have values between minus 32,768 and positive 32,767. With a 20-bit immediate value, we can have over 1 million different values. These numbers you can see here. And as I said, we have enough room in our machine encoding scheme for up to 256 format A instructions, and for the remaining formats, B, C, and D, we can have as many as 63 different instructions. Here is our add instruction, which is a format A instruction with its 3 registers. In general, you can have up to 4 registers for format A instructions. The assembler will check to make sure you have exactly the right number of registers for the add instruction. It requires exactly 3, and the assembler will complain if you try to put a 4th register in there. But some instructions have all 4 registers, and some have only 3 or 2 or 1. Here's the add immediate instruction, and it's encoded with the registers first, separated by commas, and then the immediate value, so in this order. There's some flexibility. Other instructions are encoded in assembly language in a slightly different format, but they're basically the same. And you have similar things for format C and D instructions. With the Blitz assembly code, we always put the destination on the left. And you can kind of imagine that this is mimicking the order that you would find in high-level source code. For an example, here's an assignment statement. When encoded in assembly, you'd have the same order, so the destination is first, if that helps you remember the order of things. This trick also works for branch instructions. Here's a branch if less than instruction. We'll talk about branch instructions later, but in a source code, you might have something like if x is less than y, go to some label, and in assembly language, the order is the same. Now let's go through some of the more common instructions, starting with the arithmetic instructions. We've already seen the add and the add immediate instructions, which I'm giving more symbolically here. We also have subtract, multiply, divide, and remainder instructions. There's a negative instruction. Again, this is a format A, but it only uses 2 registers, so it takes the value in register 1 and negates it, puts it into register D. For the logical operations, we have and, or, exclusive or, and not. And immediate have similar forms to the add instruction, and likewise for or and or immediate, exclusive or and exclusive or immediate. Bit not has a form like the negate instruction. And we also have a logical NOT. Okay, bit NOT flips all the bits in register 1 and puts them in the destination register. Logical NOT takes a look at what's in register 1 and asks whether it's 0 or not, and then moves in either a 1 or a 0 into the destination register. This question mark colon notation you might be familiar with means if this is true, then do this. Otherwise, if that's true, then use that value. There's a move instruction and a move immediate instruction. The first moves the value from one register into another register, copies the value, and the move immediate instruction moves a value into a destination register. There are a number of instructions to shift data. For example, the shift right logical instruction and its other instruction, shift right logical immediate, take a value from a register and shift it to the right a number of bits. And the amount to shift could be in a second register or an immediate value specified directly. There are also instructions for shifting left and arithmetic shifting as well. There is a rotate instruction which takes a value in a register and moves it into register D after rotating it around. And by rotating it, we mean, for example, when bits are rotated out of the right end or the least significant end, they go around and get shifted into the most significant end. So here's an example of shifting 5 bits to the right. Now let's talk about sign extension. Take a look at this example byte. It's a representation of the number 5, 101, with the leading bits being 0. By sign extension, we mean taking the most significant bit and just copying it into the upper bits of a larger value. So here we're sign extending a byte into a 64-bit value. With a negative number, the most significant bit will be 1. And here we are sign extending a negative 53, that's how this is represented, into a 64-bit double word by copying the sign bit into the upper bits. So we have instructions that do this. So we have sign extend byte, half word, and word, and basically they just do exactly this. The first one sign extends a byte into a double word, and then a half word into a double word, and a word into a double word. Now let's take a look at synthetic instructions. It turns out that some instructions are said to be synthetic. That is, there is no corresponding machine code for these instructions. So we saw one example already, the move instruction. And it turns out that's actually a synthetic instruction. There is no corresponding machine code for move. So instead what happens is the assembler translates this move instruction into a very similar instruction for which there is a machine code. So the OR immediate instruction is a normal instruction. It's not synthetic. And you can see when you OR a value with 0, you're going to not change any of the bits. So this has the effect of just copying whatever value is in R5 into register 7. So the assembler performs this translation or this transformation. And the benefit is that there are fewer machine code instructions. There is no, for example, there is no move instruction. We get by with just the OR immediate instruction. This makes for a smaller, simpler core and thereby reduces the complexity of the hardware. But furthermore, this also makes assembly programming much simpler. For example, let's take a look at the move immediate instruction, which is also synthetic. Well, the immediate value here is not limited to any 16-bit field size. In fact, you can have any value. The assembler will take a look at the actual value present and determine which instruction to use. And in most cases, it will use just a single instruction. The exclusive OR instruction with immediate value will do the job. Remember, R0 has the value 0, and when you flip bits, exclusive OR, with some value, you will get that value. So this instruction here, which is not synthetic, will do exactly what we want this move immediate instruction to do. If the value is larger and cannot be represented in 16 bits, then the assembler will choose another instruction sequence that will work. It may require 2 instructions or 3, or in the worst case 4 instructions to move a very large value into some register. Generally, 1 instruction will suffice, and often PC relative values can be used, and these will be very short. So almost all the time we will be just using 1 instruction to implement the synthetic instruction. This is something that the assembler has to do because the compiler can't make this optimization. It doesn't really know what some of these values are, particularly addresses. The compiler doesn't know where things are going to be going into memory, but the assembler and its friend, the linker, do know where things will be placed in memory, so they can make these optimizations and perform the translation of synthetic instructions into machine instructions. So in Blitz, it just simplifies everything to have synthetic instructions so that we don't have to worry the compiler with a lot of special cases that could go wrong and are opportunities for bugs. Next, I want to mention 5 instructions that are used by the assembler primarily to support synthetic instructions. Normally, the assembly language programmer would not be using these instructions, and the compiler would not be generating them directly. They're primarily used for dealing with large constant values. Any address that occurs in the assembly language program can be done with at most 2 instructions. So all of the load instructions, store instructions, all of the branches, the calls, and move I, the move immediate, where the value is a constant address. These can all be done with at most 2 machine instructions. In fact, most everything can be done with 1 or 2 instructions. But occasionally there will be constants that are extremely large and will require additional instructions. So I'm just going to present these instructions here. As I said, the assembly language programmer would not be typically writing these instructions, and the compiler would not be generating these instructions, but they are used in conjunction with the other main instructions, the load, store, branch, calls, and so on, to achieve the result when the immediate literal value is greater than 16 bits. Now let's take a look at the call, return, and jump instructions. These are used for calling and returning from functions, and for invoking methods, and for control constructs like while loops and if then else. We have 5 different instructions, and they are all synthetic, and in a second I'll talk about how the assembler will translate these into actual machine code. But first let's just look at each of these. The call instruction takes an address, and there's a jump instruction that also takes an address, and these are synthetic. Any address in memory can be used, and generally these will be assembled into 1 machine instruction. But if the address is a long way away and a large constant is required, then it may require 2 machine instructions in order to compile each of these instructions. The remaining 3 instructions will always require just a single machine instruction. Call register basically uses the address from a register, and so this is useful when the target address is computed at runtime. This would be useful for invoking a method, for example, where you have to examine the object to determine exactly which implementation of a method you want to invoke. The jump register instruction might be used for a switch statement where you look at a particular value and jump to the appropriate code based on some kind of a jump table or so on. Finally, there's the return instruction. Okay, here are the machine instructions that are used to implement these instructions. There are actually only two instructions, JAL, which stands for jump and link, and a jump and link register version. The programmer would not normally be coding these in assembly code, and the compiler would not normally generate these. The assembly programmer and the compiler would be generating these instructions instead and let the assembler choose the correct machine code translation. Jump and link takes an immediate 20-bit value, which is added to the program counter, that is the address of the jump and link instruction itself. So it allows for what's called a PC relative jump. So if the target location is fairly close, within plus or minus 500,000 bytes, then the offset can be added directly to the program counter and the jump can be made with just one instruction. The instruction following the jump and link is the return location, and so the address of the instruction following the jump and link is stored in a register as well by this instruction. So this is used for most of the call instructions. Jump and link register is a little bit different. It's essentially the same thing, but instead of adding the offset to the program counter, it's added to the contents of an arbitrary register, and that's part of the instruction. But again, the return address can be saved in register D. If it's not needed, then the programmer or the assembler will just use R0, so the return address will not be saved. Now let's take a look at how function call and return are implemented in the Blitz system. The arguments are passed in registers, and registers 1 through 7 are used. If there are more than 7 arguments, they are passed on the stack, and I'll discuss that in a second. But generally speaking, most functions have 7 or fewer arguments. The call instruction is then used, and generally this will compile or assemble into a jump and link instruction. The return address is saved in a register, and in this case we always use register 14, which is alternately called the link register, LR. So the address of the instruction to return to, namely right here, is saved in register 14, and that's then used by the return instruction. The jump and link instruction has an immediate field of 20 bits, and this is a PC relative offset. So if the function happens to be located reasonably close, that is plus or minus 500,000 bytes, from the location of the call, then a single machine code instruction is used. It's pretty rare to have the target of the call to be further away than that. Sometimes that's said to be a long jump. But if that happens, the assembler will then translate this synthetic instruction into 2 machine instructions at most. Now, here's the situation at the function. So let's look at the simplest case first. Now, in the simplest case, we assume that the stack is not needed, that the function can do all of its computation using just the registers. We also make the assumption that this is a function that will not call other functions. A leaf function is a function that does not call any other function, so we're assuming that this is a leaf function. Recall that the call instruction saved the return address in a register, okay? And so it will sit in that register until the return instruction. We don't need to go to memory at all in this situation. So we have the code. We begin immediately. There is no instruction requirement at the beginning that we have to put in. We'll see in more complex cases that we have to execute some instructions before we can really get going on this function. But in the simplest case, we have basically 0 overhead. We have the return instruction, and whatever the computation is, and we assume that the result will be returned in register R1. The return instruction is assembled into the machine instruction JALR, and that uses an offset. Well, in this case it's 0 and a register, and in this case the assembler will supply register R14, or the link register. So basically this is just going to take a jump back to the instruction directly after the call. The jump and link register instruction also will save the return address, but that would be the address of the instruction following the return. We don't need that, so the assembler will insert R0 in that case. In a more complex function, we're going to need a stack frame for local variables and so on. So we'll begin the function with a prologue and end with an epilogue. And in the case of Blitz, the prologue will consist of 2 instructions, and the epilogue will add 2 instructions. So we have an overhead of 4 instructions for more complex cases. Essentially, we're going to save the link register. That's a store instruction. Stores it into the stack. And then we're going to reload it right before we return. We're also going to adjust the stack pointer. Okay? We're going to decrease the stack pointer. The stack grows downward in memory, so to add to the stack, to push something on the stack, we decrement the stack pointer. And then to undo that, that is to pop the stack frame, we add to the stack pointer. Here I've just repeated the code from the previous slide, the prologue and the epilogue. We see that the link register is saved on the stack and then restored into the link register from the stack directly before the return instruction. And we also see that we are pushing a new stack frame onto the stack. Okay, so here's a picture that shows what's going on a little bit more clearly in greater detail. So our stack, as I said, grows from high memory addresses toward low memory addresses. So it's growing downward in memory. So initially the stack pointer is here, and the stack has several frames on it. And on entry to the function, we decrement the stack pointer to add a new stack frame to the top of the stack. Sometimes stack frames are called activation records. And what's in the stack frame? Well, we have space for the return address. That will be a double word of 8 bytes. And then we have some space for the local variables. Perhaps it's exactly 100 bytes. The local variables are at different offsets within that stack frame. For example, here's a local variable x at some particular offset. So going back to this code, we see what happens is we're storing the link register, that is the return address, before we decrement the stack. So it's -8, that's right here. And then we decrement 108 bytes. And from then on, we can use offsets to access the local variables. And to access those local variables, it's pretty straightforward. The load instruction and the store instruction can move data from memory into a register or from a register into memory. And they require an offset and a register. So we use the stack pointer, and if we want to access variable x at offset 72, we would use 72 as our offset from the stack pointer. It's a positive offset. If there are more than 7 arguments to the function, they cannot be passed in registers, and the additional arguments have to be passed on to the stack. And the calling function, whose frame is right here, will need to place the additional arguments into its own frame, so it will have to allocate space in its own frame for these arguments. And they will be at known offsets, agreed upon offsets, in the caller's frame. And so they too can be accessed with an offset from the stack pointer that's greater than 108. So that will get us into the stack frame of the caller, so we can access those additional arguments within the function that's called. Now, Normally the stack frames are fairly small, and so the load and store instructions are synthetic and typically will be assembled into a single machine instruction. However, notice that for gigantic size stack frames, nothing special has to happen. The assembler can deal with large offsets up to the full size of memory, so the compiler doesn't need to worry about any particular limits on stack frame sizes or different addressing methods for different frames. Now let's take a look at object-oriented programming. Let's talk about how objects are represented and how methods are invoked. This is a pretty complex picture here, but we'll go through it piece by piece. First we have the data representation, and then down here we have the code that would be generated. So let's start with an object. Here is an object, and we assume we've got some kind of a pointer to this object. The object has a header word, and that's shown right here. And here are some other objects, each with their own header words. And after the header word, we have a number of fields in the object. Each field is at some particular offset from the beginning of the object. The header word points to what's called a dispatch table, and all the instances of a particular class will point to the same dispatch table. So all these objects, which are all pointing to this one dispatch table, are members of the same class. And the dispatch table is used to get to the individual methods. So these pointers are pointing to actual code. So these are, for now, let's assume their addresses to the actual code, the address of the first instruction of the method. And so there will be several methods for this particular class. So the dispatch table will have one entry for each method that can be understood by objects of this class. The dispatch table entries are each a double word, so 8 bytes. The dispatch table also has a header field, and that points to another thing in memory, which is called the class descriptor. At runtime, it's important to be able to find some information out about the file. We might need to know its name, the class's spelled out name, and maybe the identity of the source file that where it was defined, as well as the line number within that source file. Those are particularly useful for printing out coherent error messages. We might also want to know the size of instances in case we want to create new objects of this class. We also need to have information about the superclasses so we can answer questions about whether this particular object is an instance of some class or one of its superclasses. There's also a pointer back to the dispatch table. The entries in this dispatch table are actually jump instructions, okay, to the code here. So I'll get to that in just a second, but we have 8 bytes, which will contain a jump to the first instruction of method 1 in the first slot, method 2 in the second slot, and method 3, and so on. Now, let's assume we want to invoke a method. In C++, we use this notation here to call or invoke a method. In KPL and other languages like Java, we use this notation here. I'm assuming P is some variable that is a pointer to an object, and it points to the object that we're showing right here. Okay, so we're going to call method 3 from some code. And so now let's look at the code that we've got that will perform the call. Within the method, R1, the first register, will contain a pointer to the receiving object. Sometimes this is called the self pointer. In C++, it's called this. So we have to load register 1 with the pointer to the object, and we also may have some additional arguments to the method, and those will be put in registers 2 through register 7. So if we have more arguments, we put them in registers. Okay, now we're ready to look at the code that actually performs the method invocation. And essentially we have an overhead of 3 instructions, okay, in addition to what we would have in a call situation. So let's look at how these work. Okay, a second register is required, register 9 for example here, to compute the address of the method that we want to invoke, method 3. So we've got register 1 pointing to the object. Okay, so the first instruction, the load here, goes to memory and gets this pointer and moves it into register 9. So now we have a pointer to the dispatch table in register 9. Next, well, it depends on which method we're calling. In this case, we're calling method 3, and that's located at offset 24. And the compiler would know this and compute these offsets. The compiler figures out where each method will go in the dispatch tables. And so the compiler will know that at offset 24, that is the 1, 2, 3, 4th entry in the table, a jump instruction will exist that will jump to method 3. So the compiler generates this instruction, which adds to register 9 the offset. So register 9 starts by pointing to the dispatch table, and then after adding 24, it points to this double word here. Then we have the call instruction. This is a call register. So the address actually being called is in register 9. So what we do is call and begin executing code at this location right here. Remember I said that we have a jump stored in this table, that each of these entries contains a jump instruction. So we do a call but immediately jump to the first instruction of the method. The call instruction saves the return address, which is the instruction right after the call. And then we jump to the dispatch table, and that contains the jump to the method. So at the end of the method, we have a return, and the returns from methods look just like returns from functions. It will load the link register and into the program counter and jump back to the instruction after the call. Okay, so that's how we return. Now, we can accommodate long jumps with this system. In most cases, the methods will be fairly close to each other, and these jumps can be a single instruction. But in some cases, for particularly large programs, the methods may be scattered all over memory, and we may require a long jump in order to get to distant code. Well, the dispatch table contains entries that are 8 bytes. Remember that instructions are normally 4 bytes, so we can accommodate up to 2 instructions in each entry of the table. So for the vast majority of cases, we'll have just a single instruction of 4 bytes that will jump to the code. But for all other cases, 2 instructions will suffice, and they will fit within the 8 bytes of the dispatch table entry. We've already looked at the function calling and method invocation code and how that's handled by the compiler and what machine instructions are used. Let's back up and look at the conditional branch instructions. These would be used for implementing control constructs like if, then, else, and while loops, and so on. There are actually only 4 machine instructions that are used in Blitz, and there are a number of synthetic instructions, which I'll talk about next, but they are all implemented with these 4 simple instructions. We have tests for equality, not equal, less than, and less than or equal. And in each case, you have the values in 2 registers being compared, and if the condition is true, the jump is made, and otherwise execution continues with the next instruction. The instructions have room for a 16-bit offset, and this is added to the program counter, so this is a relative jump. 16 bits can hold any number between minus 32K and plus 32K, so in almost all cases, a single machine instruction will suffice for any jump. I should also point out that Blitz really favors signed arithmetic, and these comparisons are signed comparisons. I should also point out that the dot is nothing special. The opcode name, for example, is b.le. It's treated a lot like an underscore, so you don't need to really think that it's anything special. However, we use the dot for opcode names that are for machine instructions that are not synthetic. There is a similar instruction with almost exactly the same name, but without the dot, and that is a synthetic instruction, which will almost always be assembled into the single machine instruction b.eq, but in some cases it may require an additional instruction for long jumps that are not within plus or minus 32K. Now we'll look at the synthetic instructions that do the conditional branching. So here you see the basic 6, equal, not equal, less than or equal, greater than or equal. And again, they take two registers and compare the values in those registers and perform the jump if the condition is met. These are synthetic instructions, and any address in memory is allowed. So the assembler will normally use a single machine instruction if the target location is fairly close, but in cases where the target address happens to be very far away and a long jump is required, a second instruction will be included by the assembler. So we also have these instructions. The same thing, only an immediate value is present. So branch equal if the contents of this register equals the value given in the instruction. This could be any 64-bit value, and this can be any address in memory. So these are pretty general purpose synthetic instructions. We might also mention that we've talked about the temporary register T, which is register 8, as it turns out. And the assembler will use register T in instructions like this. Obviously, if this is an extremely large value and this is a long jump that requires a large address value, then we can't get by with just one instruction, and we can't get by without using another register. So the T register will be used to contain, for example, an arbitrary large value. So the programmer, the assembly language programmer, and the compiler should probably steer clear of using register T, because the assembler will use the temporary register in assembling instructions like this. There's another variation, which is testing against 0. This is a quite common thing to do. So we have branch if equal to 0, not equal to 0, and so on. And we also use binary numbers quite a bit, Boolean values, with 0 being used to represent false and any other value being used to represent true. So we have two instructions, a branch false and a branch true, which will test the register to see whether it is equal to 0 in the case of b false, or not equal to 0 in the case of branching if true. Let's look at how these conditional branching instructions can be used by the compiler to produce code for common constructs like the if-then-else statement. We'll look at the branch equal instruction. This is a synthetic instruction, so the address can be any location in memory. And what this thing does is it tests the condition, in this case equality. If the value in register 1 is equal to the value in register 2, then we will take the branch to the target address. Otherwise, we'll keep going. So let's imagine that we've got this source code, we've got some test, and the equal instruction might be used to implement a not equal test. Okay, if A is not equal to B, we want to do some instructions. Otherwise, if it is equal, we want to do the else statements. So here's the code that a compiler would typically generate for this source code. We see the branch equal instruction being used here. We assume that the values A and B, variables A and B, are held in two different registers. And if they are equal, then we want to do the else statements. So we take a branch to an else label. And here's the else label, and here are the statements that correspond to the else statements. And otherwise, we continue executing directly after the test, doing the then statements. So here are the instructions that correspond to the then statements in this construct. These are symbolic labels, and these can be used in any assembly language program. Here you're using them as a target address for different instructions like the branch equal or the jump instruction. Here they're being used to label instructions elsewhere, and the presence of the colon is used by the assembler to indicate that this is a label. So when you're using an identifier to label a particular instruction, you would use the colon. Register 8 is used as a temporary register. We can call this register R8 or T. The assembler will accept either spelling, and we probably would prefer T for this register. The assembler will make use of this register more or less silently without any fuss when it assembles synthetic instructions. Some synthetic instructions may require an additional register. For example, the branch equal immediate. That instruction would use the T register if the immediate value happened to be extremely large. Because the assembler may be using the T register from time to time without it being mentioned explicitly in the program, assembly language programmers are probably recommended to avoid using this register directly. A compiler may use the T register in a few cases, but only when the compiler can be absolutely sure that no synthetic instructions would interfere with this register, and it can be sure that the assembler will not implicitly be using the T register in ways that would conflict with how the compiler uses it. Blitz has some testing instructions, which we'll look at next. Typically, the Boolean value of true or false will be kept in a register, and false will be represented with 64 bits of zeros, and true will be represented with 64 bits with 1 bit set. In languages like C, we sometimes see the situation where we have a value other than one of these two, and that is typically interpreted as true, although I should say that that's gotten a lot of C programmers into trouble. If you have two different representations of true, then sometimes logical operations like and, or, exclusive or don't work as you would expect. Okay, the basic instructions for testing are listed here: equal, not equal, less than or equal. What these do is they compare the values in two different registers and then store a Boolean result, either false or true, into the destination register. There are variations of these instructions. In some cases, we want to test against an immediate value, so the test EQI, not equal I, less than I, and so on. These instructions take an immediate value, and again, they compare it to the register and set register D to either a 0 or a 1. There is also a 0 variation, so we're testing the value in a register against 0. The Blitz architecture contains load instructions to read data from memory into a register, and store instructions to store data from registers into memory. Let's look at the load first. The basic instructions are load B, H, W, and D for byte, half word, word, and double word. They take an address and move data from that location in memory into a register. The value, in the case of byte, half word, and word, will be sign extended to 64 bits and loaded into the register. As we've said before, Blitz is biased toward signed data, and so everything is always kept in signed form, and so we sign extend short values into longer values. There is a variation on these instructions where the address is given by an offset and a register. So this is an immediate field in the instruction, and it's added to the contents of the register to determine the actual address from which to fetch data. The instructions listed here are synthetic instructions, and so the address can be any address in memory, and the offsets can be any value here to access any address in memory relative to some pointer. So they can be large values. Almost all offsets are small, so generally speaking, only one machine instruction is required to synthesize these instructions. Large offsets are okay, and the assembler will synthesize more than one instruction if necessary, but large offsets and large addresses are relatively rare. So generally we get by with a single machine instruction for every load and store instruction. Here are the store instructions, and they're symmetrical. Again, you can either specify an address or an offset from a register. And we have byte, half word, word, and double word variants of these two addressing formats. In keeping with the Blitz philosophy of putting the destination on the left, you see that the source is the second operand and the destination is the first operand. Here are the actual machine instructions that are used for these operations. We've got 4 load instructions and 4 store instructions, and they take an immediate offset from a register. In most cases, the synthetic versions will be assembled into a single one of the machine instructions. Let's see how the load and store instructions can be used to access fields in an object. We'll also see how they can be used to access local variables within a stack frame in just a second. Objects are stored in memory, and here is an object that starts here, and it contains several fields. Each field is located at some positive offset from the beginning of the object. And in order to access this object, we need a pointer to it. Let's assume that the pointer to the object is kept in some register like R1. So to get data from this object, that is to retrieve the data from this particular field, we need to know its offset, and the compiler will compute that. And here's a load double instruction that moves a value from the object into a register. And here you see a store instruction which moves the value from the register back into the field in the object. These are synthetic instructions here, and the assembler can accommodate any offset, so we don't have to do any special casing in the compiler or in our assembly language programming for extremely large objects. The local variables of a function are kept in a stack frame, and the frames are kept in a runtime stack. So here we see the runtime stack. Stacks grow down from high memory. So here you see the largest memory address all the way down to 0, and the stack is growing this way. And here is the frame at the top of the stack, and it contains the local variables for the function that's currently in execution. Each local variable has a particular offset from the beginning of the stack frame, and the stack frame at the top of the stack is pointed to by register SP. So in order to retrieve the value of a variable, we would use a load instruction, and the form would involve the register SP plus an offset. And again, we don't have to do any special casing if the stack frames are extremely large. The assembler will take the synthetic instruction and generate one or possibly more machine instructions, but generally just one machine instruction. In our examples, we've been focusing on double words, and double words are the most common size of value, but other sizes can be accommodated as well, half words, words, and bytes. For example, Boolean variables will most likely be kept in a byte, which is a great savings. 1 byte is a lot less than 8 bytes. So we see other loads and stores as well as the load D and store D. The Blitz architecture contains floating point, so let's take a look at some of the floating point instructions next. Let me start by saying that floating point is really complicated, and it complicates the hardware. So the Blitz architecture makes several simplifying assumptions. First of all, Blitz only supports double precision. Single precision floating point is not supported. Second, there are no separate floating point registers as there are in most other architectures. Instead, the general purpose registers are used to hold the floating point values. And finally, the floating point instructions are optional. The architecture includes support for emulation in software for unimplemented instructions. So in some implementations, if floating point is not implemented, then when a floating point instruction is encountered, floating point add or multiply or whatever, then an exception will occur and software can complete the operation. In other implementations, the instruction would be executed directly. The payoffs of our assumptions and our simplifications, well, we have a simpler instruction set architecture, which hopefully will translate into simpler hardware and smaller hardware. Also, we have faster context switching because we don't have to save a separate floating point register file. And it just simplifies context switching quite a bit, not to have to worry about floating point as any special case. So given all of that, we can look at the instructions. We have add, subtract, multiply, and several others. And these are all register-to-register operations. Again, the operands and the result will be kept in the general purpose registers. There are no new instruction formats required to support floating point. We've also got some comparison operators because comparison is, with floating point is not the same as comparison. In fact, equality itself is not quite the same. So we have to have a separate equal operator for floating point. And we've got some instructions that allow us to convert integers to floating point and floating point numbers back to integer values. Now let's take a look at main memory. Sometimes people call main memory random access memory, RAM, and you can have different implementations. For example, you could have static RAM or dynamic RAM. All of this is main memory. We can contrast main memory with hard disks and flash. Main memory is volatile in the sense that power is always required. You turn the power off, the data in the memory is lost. Disks and flash, those are non-volatile, which means that they will preserve the data when there is no power. This is where we keep our files. Main memory is for storing code and data. Instructions have to be located in main memory before they can be pulled into the core and executed. Likewise, data is transferred from main memory to registers and from registers back to main memory. We should also note that sometimes old-timers will call main memory core, but nowadays core means processor, and very few people use the term core for main memory. My laptop right now has 8 gigabytes of main memory and 500 gigabytes of non-volatile memory, about 100 to 1 ratio, roughly speaking. The Blitz architecture limits physical memory for every core to 16 gigabytes. That might sound small, but keep in mind that's per core, so a multi-core system would have several times that much as a maximum limit. Physical memory addresses are 34 bits, which is what's exactly adequate to address 16 gigabytes of memory. We also have support for virtual memory and virtual address spaces. In Blitz, the maximum size for a virtual address space is 32 gigabytes. And of course, each process will have its own virtual address space, and we may have many, many processes running at any one moment in time. Here's a picture of memory, and we're showing the entire physical memory space from address 0 all the way up to some maximum number. And each byte of memory is represented by a rectangle, and they're numbered with addresses 0, 1, 2, and so on. Here is a double word of data. You can see that there are 16 hex digits or 8 bytes, and each byte is stored in 1 byte of memory, and they're stored in so-called big Endian order. In other words, they're put into memory in the order in which they appear, like this. And the address of this double word in memory would be the address of the first byte of the 8 bytes. In Blitz, we have an alignment requirement. Okay, a byte-sized data can go at any address. There is no requirement for byte-sized data. But for half words, which are 2 bytes long, the address must be divisible by 2. In other words, it must be an even address. For words which are 4 bytes long, the address must be divisible by 4. And for double words, the address must be evenly divisible by 8. If you were to look at addresses that meet the alignment requirement in binary, you'd see that the half-word aligned addresses end with a binary 0 bit. Word addresses end with 2 bits that are 0, and double word aligned addresses end with 3 0 bits. Blitz is a big Endian architecture. If you don't know what the term big Endian means, then you can just skip this slide altogether. Big Endian is in contrast to little Endian, and it has to do with the order in which bytes are stored in memory. On the previous slide, I showed you how a double word is stored in memory in the Blitz architecture. With a little Endian architecture, the bytes would be stored in the reverse order. The Intel architecture and the ARM processors all run almost entirely in little Endian mode. Let me take this opportunity to express my opinion about this issue. I strongly prefer Big Endian. I think it's clearly superior. I find Little Endian to be very confusing and very error-prone, and it seems to be a result of legacy decisions. I understand why Little Endian was first used in the early microprocessors, but I don't think those justifications still exist. With Big Endian, byte reordering is just not an issue. In fact, I've never really made a byte ordering bug except when dealing with Little Endian. It just is, Little Endian is very counterintuitive in my mind. As far as the hardware goes, in today's modern processors, I think the performance is identical for both. After all, the computer really doesn't see order quite the same way humans do. So this is really a human issue as to how we look at memory. The computer can order bytes any way it wants to, and it's just as fast either way. Let's look at addresses next. A moment ago I said that physical addresses were 34 bits in length. Program-generated addresses are always 36 bits in the Blitz architecture. The program counter itself is 36 bits, for example. And when addresses are kept in registers or in memory as double words, the upper 28 bits of the 64 bits is completely ignored when the value is used as an address. It doesn't matter whether it's full of ones or full of zeros. The 28 bits in the upper end are just ignored. Now 34 bits leaves 2 extra bits, and I want to talk about how those are used right now. First of all, bit 35 is a very important bit. That determines whether the address will be a kernel mode address or a virtual address. So in one case, when it's a 0, the address refers to physical memory, and when the bit is a 1, the address refers to a virtual address space. So the address is indicating a byte somewhere in a virtual address space. Okay, so that's bit 35. I'll come back to bit 34 in a second here. But here is a picture of the entire address space. With 36 bits, you can address anything between 0 and this number here, FFFF. Okay, this is 64 gigabytes of address space, because 2 to the 36th is 64 gigabytes. The virtual address space when bit 35 is a 1, indicated right here, is in this region here, the upper region. When bit 35 is a 0, okay, when this bit right here is a 0, you're talking about a physical address. And that is further subdivided into halves, and that's what bit 34 is about. It determines whether it's a physical memory address. So this is where our limit of 16 gigabytes for main memory comes. Or if bit 34 is a 1, it indicates that we've got an address that's part of the memory mapped I/O region. I/O devices will be located in this region here, and any load or store to an address within this region will be directed to a memory mapped I/O device. We may also have some read-only memory mapped into this region as well. In addition to the general purpose registers, the Blitz architecture has a number of control and status registers, which we abbreviate to CSR. There are 16 of these control and status registers, and each is 64 bits. These registers have fixed meanings, and they're used to control the processor in various ways. They have special names, and in Blitz, the name of a CSR always begins with CSR underscore. The assembler recognizes these names, and so that's how we refer to the registers. In any architecture, a particularly important register is the status register. In Blitz, it's called CSR underscore status. Here are the instructions that we use to directly access the status registers. We have an instruction CSR read, write, set, clear, and swap. These instructions are encoded using the formats that we've seen before. Let's take a look at the read instruction here. It can move a value from any CSR into a general purpose register. In this example, we're moving the value in the status register into register 3. In the machine code encoding for this instruction, each register requires 4 bits, so we've already seen that the general purpose registers are encoded in the logical systematic way. The control and status registers are also encoded with 4 bits. The status register happens to be the fourth, or I should say the fifth, 0, 1, 2, 3, 4 status register, so it's encoded in the instruction as 0, 1, 0, 0. And the other control and status registers have encodings as well as their individual names. In the assembler, we use the name and not anything else. The write instruction moves a value from a general purpose register into a control and status register. This set instruction takes an immediate value, and that acts as a mask to choose individual bits, which will be altered to 1 in the CSR. In this case, the least significant bit is being set to 1. Likewise, there's a clear instruction to selectively set individual bits to 0. And finally, we have the CSR swap instruction, which does 2 things simultaneously. It copies from a general purpose register, in this example, register 4, and it copies from the CSR to a general purpose register. So it does both these things simultaneously, and that's why we call it swap. Here is a list of the control and status registers going all the way from 0 to 15. And this chart shows their names as they would be encoded in any assembly language instruction. So let's run through these things quickly. The version register is a read-only register that contains information about which version or implementation of the Blitz architecture this is. So these first 3 instructions are all read-only and cannot be modified. CSR version doesn't change at all. It's hardwired into the circuitry. The instruction and cycle registers change during execution. The cycle register counts the number of clock cycles since the system was last restarted, and the instruction counter counts the number of instructions that have been executed. since restart. Then we have the timer register. This is the time in terms of instructions executed of the next timer interrupt. So when there shall be a timer interrupt signaled, and that can be set by the operating system. Then we have the all-important status register, number 4. Then we have a number of registers: status 2, prev PC, cause, bad, and address. These are set by the hardware whenever an interrupt or an exception occurs as part of the trap handling that's done by the hardware. Then we have CSR pointer, which is dedicated to storing a pointer to something we call a thread control block. When the trap handler executes, it needs some information about where to save the state, so it needs to know where it can store things before it can proceed to use the general purpose registers. Then we have 3 registers with the names temp1, temp2, and temp3. These are work registers that can be used by the trap handler. And finally, we have 2 additional control and status registers that are as yet undefined and which might be used in a future version of the Blitz architecture. In order to be used by an operating system that implements any kind of a protected kernel, an architecture really needs multiple modes of operation, where one mode is a protected mode. In the Blitz architecture, we have exactly 2 modes. We only have 2 different modes, and they're called the kernel mode and the user mode. And here is our first introduction to the CSR status register, and 1 bit is dedicated to determining which mode the processor is running in, either kernel or user mode. In kernel mode, all instructions are allowed, whereas in user mode, privileged instructions are not allowed. So we have some instructions that are privileged, and these are the instructions that modify the control and status registers. We haven't yet talked about the TLB registers, but the instructions which modify the TLB registers are also privileged and protected. We also have a couple of others like the control and the system return instructions, which we'll discuss later. In user mode, these instructions cannot be executed. If the user mode program tries to execute one of these privileged instructions, an exception will be caused. Furthermore, the addressing is controlled by the mode. In user mode, all addresses are virtual. Bit 35 of the address must be a 1. That is, it must be an attempt to access something in the upper 32 gigabytes. And any attempt to use an address where bit 35 is 0 will cause an exception. All addresses are therefore mapped when running in user mode. Regardless of what mode we're running in, we may have an interrupt or an exception from time to time. So let's talk about these 2 terms. An interrupt comes from an I/O device or something outside of the instruction stream that's being executed. Another example would be an interrupt from the timer device. When the timer interrupt occurs, it indicates that a time slice has expired and it's time for the kernel to get in and switch processes or something like that. I/O devices can interrupt the instruction stream and require operating system assistance when the I/O transfer completes. These are said to be asynchronous since they're coming in at basically any time and not tied to a particular instruction. Exceptions, on the other hand, are tied to a particular instruction. They can arise because the instruction runs into some kind of an error condition and it cannot complete. In some cases, like page faults, it may be that the instruction can ultimately complete, but operating system help is required, so the exception needs to be handled and processed by the operating system before the instruction can continue. Examples of these exceptions include a privilege violation. If a user mode if a code running in user mode attempts to execute a privileged instruction, it's going to cause an exception. If an arithmetic problem occurs, for example, divide by 0, that will cause an exception. An attempt to execute an instruction that's not really an instruction, again, that's an exception. Also, the user mode code may want to request help from the operating system kernel, so the syscall instruction may be executed to invoke or call a kernel function. Regardless of whether we are talking about an interrupt or an exception, when the operating system code becomes active, we say that a trap has occurred and execution will be suspended from the current process. Okay, the instruction that was being executed at the time of the interrupt or the exception will be suspended, and we'll switch into kernel mode. The processor will automatically switch from whatever mode it was in to kernel mode, and some trap handler code will then be executed. At some point, there is likely to be a return to the suspended code. For example, if there's a page fault, then an exception will occur. The instruction cannot complete until the page is read in from non-volatile memory. And so the kernel has to get involved in that. And ultimately, the kernel trap handler will complete, and we can go back to the instruction that was interrupted and continue execution. In other cases, for example, a privilege violation or an illegal instruction, it makes more sense to just terminate the process, so there would never be a return to the suspended code. Now let's take a look at what happens when an interrupt or an exception occurs. Trap handling involves some actions taken by the hardware, followed by actions taken by some software. So first of all, let's take a look at the CSR status register in a little bit more depth. Previously, we showed the least significant bit, which determines which mode the processor is in, either user or kernel. The second bit is telling whether the interrupt processing is disabled or enabled. Okay, so there's 0 for disabled or 1 for enabled. So interrupts can be disabled. And if an interrupt happens while this bit is set to 0, that is, while interrupts are disabled, then the interrupt will remain pending. Processing will not occur, and instruction execution will continue as if nothing had happened. At some later time, when the interrupts are re-enabled and the bit is changed to 1, then the interrupt processing will occur and we will have trap handling. Exceptions always occur. Okay, when they happen, the instruction execution is suspended and we have trap handling. They cannot be masked, and they do not remain pending. Okay, so now let's look at what happens. We have what happens in hardware first, and then what happens in software. So an instruction is being executed and an interrupt or exception occurs. And let's assume that the interrupts are enabled, so if it was an interrupt, we're going to do this processing. Okay, if the interrupts were disabled, we would wait and not do this processing. But the hardware finishes the instruction that was under execution, if it can. In some cases, the instruction is terminated because of the error condition. But in the case of an interrupt, the previous instruction is executed to completion. Then the mode is changed to kernel, and the interrupts are disabled. In other words, these two bits in the status register are altered to 1 and 0. Then the hardware will save a bunch of information about the current state of the processor. The program counter is saved in the pre-PC. Cause will be set to a number, which will indicate what exactly is the nature of the interrupt or exception, which interrupt or which exception has happened. The status register, that is before the bits are altered, will be saved in the CSR register called stat2. And we have some other information that will be saved, and the exact nature of this information will depend on which interrupt or exception has actually occurred. And finally, the program counter will be set to this fixed value. Okay, this is part of the Blitz ISA. This particular number is where the global trap handler software will be. So after the hardware does these actions, instruction execution will resume. And what will happen next is that the instruction at this location, which is the first instruction of the trap handler, will be fetched and executed. So the software that's located at this address is called the global trap handler. And its job is to save the state of the interrupted process and to dispatch to the specific trap handler function. And maybe at some later date, the trap handler function that dealt with the particular interrupt or exception will return to the process. Maybe the process will be terminated. It depends on the nature of the exception or the interrupt. But in any case, the information will have been saved so that we can have a complete return to the interrupted instruction stream without any problems. One type of exception is the system call exception. This is triggered by the execution of a syscall instruction. So here we see the assembly language for that instruction. We've got the opcode, and we've got a single operand, which is an immediate value. And the user mode process can use this instruction whenever it wants to invoke a kernel function. So from time to time, user code will need to access operating system functions, and that code will execute the syscall instruction, and that will result in a system call exception happening. The global trap handler will be invoked, and it will be dispatched to a particular operating system function that will satisfy the needs of the user program, and then execute a system return instruction, a sysret instruction, to get back to the user mode code. The system call instruction requires a single operand, which is an immediate value, and that must be in the range from 0 to 1023. In other words, we have 1024 different kinds of system calls that can be covered by this particular instruction. The arguments are passed in registers 1 through 7, just like in a normal function call argument passing, and the result will be returned in register R1. So the parameter passing follows the normal conventions. The immediate value, okay, one of these 1024 numbers, makes for very fast dispatch to the most common 1024 operating system calls. So the immediate value that appears in the instruction is placed into the CSR cause register. Actually, it's multiplied by 8 to make the dispatching extra fast, but essentially that number goes into the cause register, and then the global dispatch will use the cause register's value to determine which function to jump to. So that makes it very fast to dispatch to the most common operating system calls. And then later, in the trap handler code for the particular system call, the operating system code will execute a system return instruction. This is a privileged instruction, so it has to be executed by the operating system. And what it does is it restores the program counter, and it restores the CSR status, and basically returns to executing the code. So the next instruction after the system return instruction will be the instruction that followed the system call instruction. Now let's talk about several exceptions that are concerned with error conditions. The Blitz philosophy is to catch as many errors as we possibly can. We really would like to catch any and all errors that occur at runtime. And the reason we want to do this is because we just want our software to be more robust and our systems to be more reliable. And we try to do as much error checking in hardware as we possibly can. We want the error checking to be fast, and so putting it in hardware means that it's executed in parallel, and so it doesn't have a great performance impact if it has any impact at all. Another important reason to put the error checking in hardware as opposed to software is because it's guaranteed to happen. It will be done. The error checking will occur. If you rely on the programmers to perform error checking tests, well, sure enough, they won't always happen and you'll get problems. In fact, the legacy philosophy is to emphasize speed of execution over error, over anything. And this is really pervading languages like C. And it's true that we have really fast computers as a result of this, but we're also beginning to see errors cropping up and unexplained behavior and so on. And Blitz is an attempt to address this by looking at a different approach. And so when an error occurs, we want to raise an exception. So let's look at the first exception, which is the arithmetic exception. First, there's divide by zero. Everybody is familiar with this problem, and this will cause an arithmetic exception. In traditional processors, overflow is simply ignored, and as every C programmer knows, if you add two numbers together, you may get an incorrect result, and there won't be anything to let you know that that has happened. So unless you are a great mathematician and do a thorough numerical analysis on your program, you're really taking a substantial risk when you use a language like C. With Blitz, our philosophy is completely different. We really want to catch all arithmetic overflows, so everything is checked. Okay, and overflow is always considered an error. You know, there's never a case where when you add two numbers and you get something that is not their sum, that it's okay. That's a problem. We're using 64-bit arithmetic for all of our arithmetic, so overflow is rare. It requires really big numbers. So, you know, it shouldn't be happening, and when it does, it's always an error. When an arithmetic exception or any one of these exceptions occurs, then software will get control, and we have information about where execution was and so on. So we can print out a nice error message about what exactly went wrong. So let's look at the load and store exception next. The load and store operations are required to be properly aligned, and if they are not aligned, then we will have an unaligned load store exception. Almost all load and store operations are okay. Anything generated by the compiler is going to be properly aligned. But it's possible that certain programs will have unaligned load and stores for addresses that are not aligned. So we need to have support for this. And the software can handle this exception in two ways. Perhaps we can just forbid it altogether, but there's also support for emulation of unaligned loads and stores. So it's very possible that the trap handler will perform the unaligned load and store and then return to the instruction execution without any problem. Arrays are frequently used, and array indexes can be out of range. As we know, buffer overflow errors or overrun errors have been a common source of all kinds of problems, both errors and opportunities for malware to gain control. In the KPL language, all array accesses are checked, so we make sure that the index is valid. And in order to reduce the amount of overhead for that, there's a special instruction called the check A instruction, which basically just checks an index to make sure that it's in range. And if not, we get a very specific message that an array index went out of range. And finally, we have the null address exception. Very often programmers use null pointers to deal with special cases. And then the error occurs when they attempt to use a null pointer for a load or store, or perhaps a branch. With the Blitz architecture, every branch instruction, every call instruction, or load, or store instruction is checked. And if you happen to be trying to use an address which is 0, then this exception will occur. So a null pointer is caught whenever you try to use it. Now the programmer can obviously test for a pointer being null if they want to do a special case and take different action. But if the programmer fails to check the pointer and it turns out to be null, then this sort of an error will arise and the exception will occur. What this means is location 0 is essentially unusable, but this is not really a problem. First of all, location 0 is not in any virtual address space, because remember they all start with addresses that have bit 35, the most significant bit, set to 1. And in any case, losing a byte or two at the beginning of physical memory with memory sizes that are 8 gigabytes or thereabouts is really insignificant, an insignificant cost to pay for this protection against the use of null pointers. All arithmetic in Blitz is done with 64 bits. When a smaller value is loaded with the load byte, load half word, or load word instruction, it's sign extended to 64 bits, and when a 64-bit value is stored in memory with a store byte or store half word or store word instruction, the upper bits are just truncated and ignored. Sometimes it's important to see whether a particular value is within range before doing such a store operation. For that, we have 3 instructions: the check byte, check half word, and check word instruction. These will take a look at the value in a register, and if the value is not within the range that's representable with 8, 16, or 32 bits, an arithmetic exception will be signaled. Also, it may be that we have Little Indian data that needs to be converted to Big Indian data. And for byte reordering, we have the instructions Indian, H, W, and D for half word, word, and double word. For example, the Indian W instruction will swap the order of the bytes in a word. This instruction can be used both to go from Little Indian to Big Indian or from Big Indian to Little Indian. Before we talk about how Blitz supports virtual memory, let's talk about virtual address spaces. Every user mode program lives in a virtual address space and cannot access anything outside of that. So every program, every user mode program, must use an address that has the most significant bit set. So all addresses used by a user mode program must range between these two numbers here. The virtual address space is broken into pages, so the operating system will allocate a number of pages for each user mode program. Most of the pages in the address space will be unallocated, but any allocated page is readable by the program. Pages may also be marked writable, and they may also be marked executable. The first pages in the address space will contain the static or global data for the program. These pages would contain variables that have fixed addresses. The stack up at the top end of the virtual address space is where functions will allocate their stack frames, so all the local variables for functions will be found in the stack. So the stack pages would also be marked writable. After the global data here, we would have the program itself, and the pages containing the program would be marked executable but not writable. The stack grows down, as we've said before, and above the program we have space for the heap. So as the program needs additional space, it can allocate things on the heap, and the heap space can be allocated by asking the operating system for additional pages in this region. In addition, the operating system may facilitate shared pages between address spaces. So one user mode program can communicate with another user mode program by reading and writing to shared pages, and those pages would also be in this region here. In addition to what you see up to here, we also have an additional region of 1 gigabyte, which is by definition always at this address. And this region is shared by all user mode programs, and it's marked read-only. It cannot be updated, and it's executable. And in this region, we would find code that is for functions that are shared by all user mode programs. So commonly used functions can be placed in this region, and that way there only needs to be 1 copy of these pages in memory. Another aspect of the virtual memory system is that the memory mapped I/O devices are each assigned to a page in the memory mapped I/O region, and those pages can be mapped into a virtual address space. So the operating system can give a user mode program access to a memory mapped page for a particular I/O device, so that a user mode program can control a device. This is controlled through the virtual memory management system. As we've said, each user mode program has its own virtual address space. Address spaces are broken up into pages, and in Blitz the page size is 16 kilobytes. Each page has a number of attributes: valid, writable, executable, and dirty, and these determine what can be done to the page. So if the page is marked not valid, the page cannot even be used by the program. It's essentially not mapped into the address space. A page could be marked writable, and the pages that are used for the stack and for the global data and for the heap would be marked writable, and the user mode program can update data that's stored on writable pages. If the page contains code, it should be marked executable. And we also have a dirty flag, so a page could be marked dirty once it's been updated. And this is not really seen by the user mode program, but it's necessary in order to support virtual memory and paging. So you have to write, the operating system has to write the page out to non-volatile storage if it's been updated, and so the dirty bit will tell whether that page has been written to, and the operating system therefore can write the page out to non-volatile memory if and only if it's been updated. The operating system will map each page of the virtual address space into physical memory, or perhaps memory mapped I/O, or not. Okay, if the page in the address space is not allocated at all, it will be invalid and it won't be mapped to anything. If it's just regular memory storing data and stack and heap and so on, and the program, it would be mapped to a page of physical memory. User mode programs may also be granted access to various I/O devices by the operating system, and if a user mode program has access to a memory mapped device, then the corresponding memory mapped area for that device will be mapped into one of the pages in the virtual address space. So the user mode program can control the device by doing loads and stores to the page in its address space, in the virtual address space that is mapped to the device. Pages can also be not present, but part of the address space, but not in memory at the current moment, so they're paged out to disk or other non-volatile memory. Pages can also be shared with other processes, and there's also support for copy on write, which is a technique to avoid copying pages when new processes are spawned if you don't have to copy the page. As I mentioned, the page size in Blitz is 16 kilobytes, and this is fixed. It's not an option. In most architectures, the size of pages is variable, and this adds quite a bit of complexity. So the decision was made to fix the page size for Blitz at one particular size, and it is 16 kilobytes. And I wanted to say a few words about that. First of all, this is a fairly large size, but it has the effect that most processes, or small processes, won't need very many pages. For example, with only 8 pages, you can have an address space that's 128 kilobytes. This is important because the more pages a process has, the more TLB registers are required. I'll talk about those in a minute, but by having a larger page size, you reduce the pressure on the TLB registers, and that is going to reduce the context switch time. The next thing I want to mention is that a process requires a page table. The page table is an operating system data structure that tells how the virtual memory address space is mapped out. With a single level table, we can have a virtual address space of up to 32 megabytes. And by single level, what we mean is that we are storing a bunch of page table entries, and we're storing, in fact, as many page table entries as we can into a single page. So we require one extra page for the entire page table for any program that goes up to 32 megabytes of address space. And really, this is quite a large program, and we expect most of the programs to be under 32 megabytes. So a single level page table is a beautiful thing. And for really large programs, and there will always be a few of these, we can get by with at most a two-level page table. With up to 2 levels in the page table, we can access all of the 32 gigabyte address space. Next, let's take a look at virtual addresses in Blitz. Recall that all addresses are 36 bits. Virtual addresses always have this bit, the most significant bit, set to 1 to indicate that it's a virtual address. The remaining 35 bits are divided into 2 fields. The lower 14 bits are the offset into the page, and the 21 bits above that is the page number, or the virtual page number. The upper bits are ignored in any 64-bit value that's used as an address. So now let's take a look at a page table entry. 64 bits are used for each page table entry, and we have the address space identifier, virtual page number, physical page number, and a number of bits. So let's start with the virtual page number. The 21 bits from the virtual address will be used to locate a page table entry, and that 21 bits will be translated into 21 bits that will indicate a physical page number when that page is mapped into physical memory. The bits here are the valid bit. That's the bit that tells whether this is a valid entry or not, and whether it has this form or not. The dirty bit, which indicates whether the page has been modified. Every time a store occurs to a virtual page, the dirty bit for the page table entry is changed to 1. And then we have the executable and the writable bits, which tell whether this page can be used for storing code, that is, whether a fetch can occur from the page. A fetch can occur if the page is marked executable, or whether a store to the page is acceptable. And a store can be only done to pages that are marked writable, otherwise an exception will occur. And finally, you see the address space identifier here. This is 16 bits that indicates which address space we're talking about. So this page table entry refers to a particular address space, and at any one time there can be, well, up to 64K different address spaces as indicated by a 16-bit integer. So to support virtual address spaces, the Blitz architecture uses 16 bits. So every virtual address space is assigned a unique 16-bit number, which allows up to 64,000 virtual address spaces at any one time. If the operating system is going to support more than 64,000 processes running simultaneously on any core, then it's going to have to fall back on a more complex algorithm and reuse these numbers. But for any reasonable situation, the hardware will support up to 64,000 virtual address spaces conveniently and quickly. So now let's take a look at the status register in full detail. This is the CSR status register, 64 bits, and we've already discussed the kernel mode bit and the interrupts enabled bit. There's also a single step bit, which is used to control single stepping. I'm not going to go into that in this video. And then you have some bits that are used by the floating point instructions. You have a couple of bits here that dictate how certain instructions will round their results, and this is all part of the IEEE floating point standard. You also have some status bits that indicate certain conditions, like whether overflow has occurred or not a number, things like that. Then you have a bunch of unused bits, and finally the status word contains the 16-bit address space identifier. And so when a user mode process is running, the status register contains the ID number for the address space that that user mode process is running in. And so this is used in the matching of the page table entries when an access to memory is made, either when an instruction is fetched or whether a load is trying to retrieve information from the address space or a store is trying to send information to an address space. To efficiently support virtual memory and the mapping from virtual address spaces to physical memory, the Blitz architecture includes TLB registers. TLB stands for Translation Look-Aside Buffers. It's kind of an awkward name, so we just say TLB registers. So there are a number of these registers, and the exact number of TLB registers is variable. So you can imagine that there are 8 registers, or perhaps a particular implementation of Blitz will have many more registers. That's really a performance question and not really an architecture question. Each TLB register is 64 bits, and we'll talk a little bit about how they work. So we've mentioned the page table, and we've got some sort of a data structure that describes each page in a virtual address space. Well, the idea is that each TLB register contains a single page table entry. So each register contains a TLB entry. And you can think of this as a cache for the most important entries from the full page table. Of course, a program is only going to access a small number of pages at any one time. That's the working set concept. And so only a small number of page table entries are needed at any one point in time. And so essentially we're caching the most important entries from the full page table in the TLB registers. So whenever the processor encounters a virtual address, which is at least once per instruction, because of course every instruction has to be fetched, and for loads and stores, there's also an access to the virtual address space. What the processor will do is search all the TLB registers looking for a match. The TLB registers are associative, so essentially all the registers can be searched in parallel by the hardware all at once and quickly. And the hardware will identify the entry that matches. Okay? It looks for a TLB register that contains an address space identifier that matches. So it looks at the address space identifier from the status word and matches it against the TLB entry. And it also checks the valid bit, because if the page is invalid, it indicates that TLB register is not in use. And then finally it looks at the virtual page number to make sure that the page number of the address that's being needed is matching the address in the TLB entry. And if there is a match that's found, then the hardware will go to the TLB entry and get the matching entry's physical page number. Okay? Remember that the virtual address contains a virtual page number as well as some other bits. And here's the page table entry Okay, it's got the virtual page number. So each of the TLB registers contains something with this format, and we look for a match where the address space identifier from the status register matches these bits, and the virtual page number from the address matches these bits. And that gives us the physical page number and the bits as well to check for valid and so on. So if a matching entry is found, we use the physical page number and concatenate it with the offset to get the actual address to use. In addition, we check the writable and executable bits to make sure that this access is legal. And if anything goes wrong, basically we'll signal an exception. So there are a number of hardware exceptions that will happen if, for example, there's no matching entry or there's a violation of the writable or executable bits. And that will give the operating system control. When the exception occurs, the global trap handler will be invoked, and the operating system kernel will handle that exception somehow. It might abort the process if, for example, the process is trying to write to a page that's not writable, or if perhaps the page is just out on disk or something like that. It would be invalid. There would not be an entry in the TLB registers. And so the operating system would figure out which page is needed and read it in from the non-volatile memory. Before we describe the individual TLB instructions, let's sort of review what's going on here. Remember that the TLB registers are each 64 bits, and each one contains a page table entry. And the number of TLB registers is variable. When an address is used in an instruction, it's a virtual address, and the hardware will search for a matching entry in the TLB register, searching them all at once. So the TLB is essentially a cache memory. It's an associative memory. The lookup happens in parallel for all the entries. And it may be the case that there is no matching entry. There's no matching entry that's valid in the TLB registers. In that case, the operating system will get control, and the operating system has to deal with the issue. It might have to search the full page table. It may be that the page table entry exists and that the page is perfectly valid and the access to that address is perfectly okay. There just wasn't enough room in the page table registers for that particular entry. So the operating system has to find an entry in one of the TLB registers and replace it with a new entry for the page that's being accessed. So there's quite a bit of work going on here with the operating system figuring out what to do when there's not a match. But one common case is that the page is in memory, everything's okay, it's just that that entry is not in the TLB register file. Okay, this kind of goes back to the idea of the working set. Okay, remember the main idea with the working set is that data that was used recently is likely to be needed again in the near future, and that data that has not been used recently is not likely to be needed again anytime soon. You know, programs do not behave randomly. They tend to do the same thing over and over again. So most likely we'll have the entry we need in one of the TLB registers and there won't be a problem. So most of the time the operating system will not be involved directly, and the access to memory will happen very quickly. So we would like to have that situation as often as possible, and the more we have to go into the operating system and mess with the TLB registers, the slower the program will run. So let's take a look at the TLB register file next. If the page table entry we need is in one of the TLB registers, then the access can go ahead and occur quickly, all in hardware. But if the entry is not in one of the registers, then the operating system is going to have to become involved, and it will have to select one of the existing entries and evict it and move in a new page table entry into that register. Now, we want to get rid of an entry that's not likely to be needed anytime soon. So we have the concepts of the most recently used page table register and the least recently used register, often LRU. So given the working set idea that data that was used most recently is likely to be needed again in the near future, we'd like not to replace the entry that was most recently used. In fact, the best thing to do is to replace the entry that was least recently used. That is, it was used furthest in the past. So we're going to think of our TLB registers kind of like this. We can number them 0 to, well, it depends on how many we have. Let's say we have 8 of them. And what the hardware will do is every time a TLB register is used, it becomes the most recently used entry. So the hardware will move it to the top of the file, and everything else will get shifted down. Or more precisely, everything that was above it before will now be moved down. So this basically happens every time a virtual address is translated into a physical address, and the thing at the top, the entry at the top of the register file, will be the most recently used entry, and the thing at the bottom is the least recently used. So that's the entry we want to replace. Okay, so whenever a page fault occurs and the operating system determines that the problem is that there is not an entry in the TLB register file, it needs to add a new entry, and so it needs to replace one of these entries. And the logical one to do to replace is the one at the bottom, the least recently used. So to do this, there is an instruction called TLB push. Okay? So the idea is that a general purpose register contains a new page table entry, and the operating system will execute this instruction. And what it does is it just essentially pushes this new entry onto the top of the stack of registers, and the one that was at the bottom, the least recently used entry, will just get dropped off the bottom and disappear. So now that you understand the TLB push instruction and how the TLB registers work, we can mention the other TLB instructions, which are pretty straightforward. We have a read and a write instruction to move data into arbitrary TLB registers. We also have a set and a clear instruction to set and clear bits in a TLB register. The TLB delete instruction is needed for whenever a virtual address space is destroyed. So we basically are getting rid of an address space because a program has finished execution, and we need to maybe reuse the address space identifier. We want to invalidate any and all TLB registers that apply to that address space. So that's the TLB delete instruction. And finally, there's an instruction called TLB check, which is used to determine what would happen if a given virtual address were to be used. Sometimes the operating system is wanting to go to the virtual address space and get a byte from the user's memory, and the operating system would like to check and make sure that there's not going to be a fault before that. So the TLB check instruction is provided for that use. So now let's look at what happens when the kernel accesses data that's in the user's virtual address space. Consider the situation where the user process makes a system call and needs to pass some data to the kernel. Perhaps it's a large amount of data and cannot all be passed in registers. Or imagine that the kernel needs to return some data to the user program and it won't fit in registers. So in either case, the kernel needs to have access to the user's virtual address space. Well, there are several different ways that this can happen. In one approach, the kernel is running in its own address space, probably the physical address space, and the user mode code passes a virtual address to the kernel. The kernel then has to mutate or map that virtual address into an actual physical address, and then it can access the physical locations in memory. Another approach is where the kernel code is itself mapped into the user's virtual address space, and so the code handling the system call basically is living in the same address space as the user process. So address mapping is occurring. Blitz has a somewhat novel approach to this problem, and I'll describe it here. Basically, the kernel runs in physical address space, the user mode runs in the virtual address space, and the kernel can use addresses just directly as they are without doing any kind of work at all. It sees that the address is a virtual address space because bit 35, the most significant bit, is set, but the kernel doesn't really need to do anything in particular. It just uses that address. Presumably the address space ID is still sitting in the CSR status register. Well, regardless of whether the processor is running in user mode or kernel mode, address mapping will occur. So the processor performs the address mapping using the TLBs. So essentially there's no performance penalty. The address mapping occurs automatically, just like it does for the user level process. And so that works pretty well for any normal access to user space by the kernel, assuming there's not a fault or anything. We think this approach is somewhat novel and perhaps a little bit simpler. Now let's look at a few instructions that are not covered elsewhere. The align and inject instructions are rather detailed in what they actually do, but they're provided for the specific purpose of supporting the emulation of unaligned load and store instructions. While the details are complex and complicated, essentially they just move bits around. The no-op instruction is a synthetic instruction. It just does an add. The debug and breakpoint instructions are used to support debuggers. There's a debug exception and a breakpoint exception, and when these instructions are executed, they will cause that exception to occur. If you are emulating the Blitz machine, it's also possible as an option for the debug instruction to pop you into the emulator's debugger. There is a sleep 1 instruction and a sleep 2 instruction for switching the processor into various power saving modes. And there are a couple of instructions for dealing with addition. In the case of the add OK instruction, the instruction checks to see whether overflow would occur if the add was executed and returns a Boolean result. In the case of the add 3 operation, the add, a 64-bit addition, is done without any overflow exception when the result is not representable as the valid signed result of adding two signed numbers. So this would be used in a number of situations, particularly for supporting unsigned arithmetic. In this video, I believe I've covered the entire Blitz architecture and mentioned all of the instructions. But I am certain that I have not included every important instruction that you'd like to have in the architecture itself. So the final two instructions I want to look at are the control and control U instructions. They're basically the same. Each takes a register and an immediate value and puts a result in register D. The control instruction is privileged, so it can only be executed in kernel mode, while the control U is not privileged and can be executed in either user or kernel mode. And the idea with these instructions is that it's up to the hardware implementer to define them. these are placeholders essentially for some functionality that is not included in the Blitz architecture. The Blitz architecture, as we've described here, is completely adequate and sufficient for implementing the KPL language, but there may be many other functions that you'd like your core to do. And in order to incorporate additional instructions, one approach is to use the control and control U instruction opcodes. So the way this works is that the immediate value is intended to act as sort of a supplemental opcode. And the register listed as the source register 1 operand can provide data for the operation, and any result that is computed can be placed in the destination register. And how might this be used? Well, these instructions might be defined in a simple microcontroller for embedded applications to run I/O pins. Digital I/O pins might be controlled. For example, a control instruction might set some output pins that would maybe drive LEDs, and the input digital lines would be read into the destination register, perhaps sensing switch positions and so on. It may be that your hardware needs to have some specific control over the cache or pipeline, for example, to flush caches or to sync caches on a multi-core system, something like that, or to send signals to other cores. This might be a use for a control instruction. There may be also a need to perform some specialized computation. In particular, high-speed encryption is important. Well, encryption itself is important, and it's important to do it with specialized hardware because the operations are sometimes rather time-consuming. And so this is another situation where a control instruction might be designed to take care of that functionality. Well, I think that's about it. I believe I've covered the entire Blitz architecture, so thank you for watching.